day, everyone. My name is Muhammed Suleiman, MSK. Today, we shall be discussing number days in mathematics. When we talk about days, we are simply referring to smallest unit of counting numbers. Numbers can be counted in many bases. We are much more familiar with base 10. Why? Because we are naturally born with 10 fingers on our hands, but there are other bases of which numbers can be counted. Base 9, base 8, 7, 5, 6, 3, 2, 1, as many as possible. So today, we're going to discuss as many examples as possible on other bases, especially base 2. No computer, working base 2, that is the input as well as the output. So, let's talk about basic operation on number bases. The basic operations on number base. For example, in base 2, for example, in base 2, note in base 2, 1 plus 0, so let's do something as 1. 2, 1 plus 1, something as 1, 0. Some call it 10, but this is 1, 0. Then number 3, 1 plus 1 plus 1, something as 1, 1. Later we see why so. So with this, we can simplify as many number base as possible in base 2. For example, suppose we are asked to simplify 1, 0, 1, 0 plus say 1, 0, 0, 1, all in base 2. How do we start? We start with 0 plus 1, something as 1. 1 plus 0, still something as 1. 0 plus 0, something as 0. 1 plus 1 is something as 1, 0. So what we do, 1 plus 1 is 2. How many bundles of 2 are there in 2? It's 1 remainder 0, remainder carry 1. So by conversion, 1, 0, 1, 1, 0, 1, 0, is something as 10 in base 10, while 1, 0, 0, 1 is something as 9. So this is something as 10 plus 9, and 10 plus 9 is 19. So this is 19 when converted to base 10. Another example, suppose we have example 2. Supposing this is 1, 1, 1 plus 1, 0, 1, all in base 2. Remember, the base is the smallest unit of counting numbers. This is 1 plus 1. 1 plus 1 is 1, 0. We already settled it. 1 plus 1 is 1, 0. We write 0, carry 1. We have 1 carry. Saying 1 plus 1 plus 0. 1 plus 1 is 2 in base 10. How many 2 are there in 2? We have 1 bundle remainder 1. Then 1 plus 1 plus 0 is still something as 1, 0. So what do? We write 0, carry 1. We still have 1 carry. Then 1 plus 1 plus 1. We have 1 plus 1 plus 1. We say it's something as 1, 1. 1, 1. So when converted to base 10, 1, 1, 1 is something as 7. Then 1, 0, 1 is something as 5. So invariably, it is something as 7 plus 5, which is 12. While 1, 1, 0, 0 is something as 12 in base 10. So these are the various ways that you're expected to handle your number bases. Some have other bases, for example, example 3. Suppose we have 4, 1, 2, say minus. This time around, we have the operator negative sign, or like we have plus, plus, minus 1, 0, 3. One will be wondering, suppose this is in base 5, this is equal in base 5. So this is no more 412. No, this is 412 because of the base. Then we are now asked to subtract 103 from 412. All we do is 2 minus 3, it can't. We borrow this. When you borrow this, what's left here is 0. To the fact that you are working in base 5, what you borrowed now is now 5. 5 plus 2, 7. Then you have 7 minus 3. The result is 4 in base 5. What's left here is 0. 0 minus 0, 0. So you have 4 left here. 4 minus 1, the answer is 3. So the result is 304. Not 304, but 304 in base 5. So, but the major problem the student normally encounter is conversion of number base. How possible can we be able to convert from one base to another? That is from natural base to other bases, or from other bases back to the natural base. When converting a number from natural base to other bases, we are expected to use a long division method. For example, convert 32 to a number in base, let's say 2, 3, let's say 4, let's say 5. Have 32 in base 10, natural base. Expecting you to convert this number from base 10, first question, to base 2. Solution comes here. We use a very long division method. Here we have the natural number on the right side, 32, while other base on the left side. So 32, 2 into 32. 2 into 3 goes 1, remainder 1, plus this 12. 2 into 12, 6, remainder 0. Always write the remainder. Then 2 into 16 goes 8 times, remainder 0. 2 into 8 goes to 4 times, remainder 0. 2 into 4 goes 2 times, remainder 0. Always write down the remainder. 2 into 2, 1, remainder 0. 2 into 2, it can go. So in this case, we exchange. We have 0, remainder 1. That tells you that 32 in base 10 is equivalent to, starting from the last remainder, 1, 0, 0, 0, 1, 2, 3, 4, 5 in base 2. Next example. We are asked to convert 32 to a number in base 3. We follow the same procedure. Example 2. Have 32 on the right side, the lower base on the left side. Say 32 goes into 3 into 32. Remember, 3 into 30 goes 10 times. Here we have remainder 2. Next again, just like 3 into 3 goes 1. 3 into 2, it can't, 0, remainder 2. They divide again, 3 into 10, it goes into 3 times, remainder 1. 3 into 3, 1, remainder 0. Then 3 into 1, it can't, you exchange this to be 0, remainder 1. So in a nutshell, this is telling you that 32 is equivalent to, starting from the last remainder, 1, 0, 1, 2 in base 3. So while considering base 2, in base 2 the highest digit is 1. You can't have a number greater than 1 in base 2. While considering base 3, the highest digit is 2. You expect to have all values less than or equal to 2. So now, with this, then you should be able to convert 4, 5, or any other number from natural base to that particular base. The next area of problem is, at times, students always find it difficult to now take otherwise. That is converting from other bases back to base 10. For example, 1, 0, 1, 2 from base 3. Maybe you may be asked to convert a number from other bases back to base 10. For example, supposing, having known that 1, 0, 1, 2 in base 3 is equivalent to 32 in base 10. Supposing we are asked to convert convert 1, 0, 1, 2 from base 3 to base 10. Remember what we said from beginning? When converting a number from a natural base, base 10, to other bases, use a very long division method, and every step, always try to write down the remainder. Meanwhile, while converting a number from other bases back to base 10, now take otherwise. Otherwise means the opposite of long division method, that is use a very long multiplication method. So the solution comes here. You have 1, 0, 1, 2 from base 3. So you assign these imaginary powers 0, 1, 2, 3, starting from the right side. So what we do, we take the number, the first digit is 1. You multiply by the base, rest of the power you assign, rest to the power of 3. You take the second digit. Suppose in exam hall, maybe in jam hall, whenever you come across 0, you can omit it. But for the sake of class teaching, you add plus 0 times the base, rest of this power, plus 1 times the base, raised to the power of 1, plus 2 times the base, raised to the power of 0. So to simplify this, remember this is some 3 raised to the power of 3. 3 times 3 times 3, the answer is 27. Okay, now we go for break. When we come back, we continue from where we start. Thank you for watching. Welcome back, everyone. Earlier before the break, we started example on conversion from other bases back to base 10. So we said did something as 1 times 3 raised to the power of 3 is something as 27, then plus 0 times any number is already equal to 0, but 3 raised to the power of 2 is something as 9, then plus 1 times 3 raised to the power of 1 is something as 3, right from indices we've seen that, then plus 2 times 3 raised to the power of 0 from indices. Anything raised to the power of 0 is something as 1. So now we simplify the values. How possible? Use something as 1 times 27. Okay. All right. 1 times 27 is something as 27 plus 0 times any number is 0. Here we have 0 plus 1 times 3, say 3 plus 2 times 1, 2. So we can easily add the numerals. So this would be the same thing as 27 plus 0 is 27, plus 3, 30, plus 2. Here we have 30 plus 2. So at the end of the day, we have 1, 0, 1, 2 in base 3 is equivalent to 30 plus 2, 32 in base 10. Another area that students may come across questions on number base is this. Having known that the value here is 2, students may be asked, look at this. Let's say example 2. Given that 1, 0, 1, let's say x in base 3 is equals to 32 in base 10. You'll be asked to find the value of x. Given that 1, 0, 1 x in base 3 is equals to 32 in base 10, find the possible value of x. X must be a positive value because all these are digits. So the best thing you do is you either convert 32 to base 3, after which you determine what is the last digit after the conversion. The last digit stands for the possible value of x. Or you now use a very long multiplication method, equate the bases. make the base on the right side equals to the base on the left side. Preferably, since we are much more familiar with base 10, convert this base 3 to base 10 so that you can solve the algebraic equation in such a way that you can be able to determine the value of x. Example, solution comes here. Here we have 1, 0, 1, x in base 3 is equals to 32 in base 10. So assigning imaginary powers, 1, 0, 2, 3. So this will be the same thing as 1 times 3 raised to the power of 3. I can omit this easily. Just take this. Then plus 1 times 3 raised to the power of 1. Then plus x times 3 raised to the power of 0 equals to 32. Why? Because we've seen this right from here that 0 times 9 equals to 0. So that is why any number times 0 is 0. So there's no need of taking this into the solution. So we have this is something as 1 times 27 plus 1 times 3, then plus x times 1 equals to 32. Why? Because any number raised to the power of 0 is something as 1. A number raised to the power of 1 is something as that number. So in this case, we have 1 times 27 as 27 plus 1 times 3, 3 plus x times 1 is x equals to 32. So further simplification yields that 27 plus 3 equals to 30 plus x equals to 32. Collecting like terms, the like term shows that x will be equals to 32 minus 30, and 32 minus 30 equals to 2. That shows that the value of x here equals to 2, which is the same thing as the 2 right from the beginning of the equation. Thank you for being part of the program, and thank you for watching. In this very example, you notice that one of the digits from base 3 is unknown. So at times, the base may not be given to you, and we may be asked to determine the value of the base. For example, let's take another example. Okay, 132. Number 3, supposing we have given that 132 in base n equals to 30 in base 10. Find the value of n. Unlike example number 2. In example number 2, we have a missing digit. While in example number 3, we have a missing base, n. And always try to write the base quite below the number. Alright, solution comes here. Here we have 132 base n equals to 32 already in base 10. Since in base 10, there's nothing to write in base 10, still the same thing as 30. Okay, so remember the idea, long multiplication method. Before then, assign these imaginary powers. 0, 1, 2, 3, 4 continuously. We take the first digit, and the first digit here is 1. Take 1, we multiply by the base, raised to the power of assigned digit. Then plus the next digit here is 3 times the base, raised to the power of the assigned digit. Then plus 2 times the base, which is n, raised to the power of 0, equals to the natural base, which is 32. Even if you convert 30, to base 10, you still have about 30. So the idea is to make both sides to be on the same base. The right side in base 10, likewise the left side in base 10. Okay, so we have n times 1 times n raised to the power of 2 remains n raised to the power of 2, then plus 3 times n, this is 3n, plus 2 times 1, because n raised to the power of n is something as 0 is something as 1 equals to 30. So to simplify further, this will be something as n squared plus 3n plus 2 minus 30 equals to 0. Seeing that the highest degree of the variable is 2, this will now yield to quadratic equation. So in this case, remember the general form of quadratic equation is always ax squared plus bx plus c equals to 0. So now, try to make this to be form of quadratic. That is n squared plus 3n. 30 minus 2 is 28, but 2 minus 30 will yield minus 28 equals to 0. Okay, so to simplify this, assuming I'm in the exam hall, I wouldn't like to waste time. There are many ways, but the best way, you open a bracket to the fact that the coefficient of variable square, here is unity. Here you assign nn. So we think of two values that are multiplied so that the result equals to 28. And when you simplify the values, the result equals to 3. You have 28. Think about 28. 28, 7 times 4. Look at this. Can enter 7 here, can enter 4 here. The next thing you think of is this. This is positive. Meanwhile, the larger value will be having a positive sign. Having a negative sign, the smaller value will be having a negative sign. Why? Because 7 minus 4 is 3. So here we have either n plus 7 equals to 0 or n minus 4 equals to 0. Possibly, this will yield a negative result. Then, this can never be a negative value, so here we take n equals to 4. This is the result of the unknown base. That is 1, 3, 2 in base 4 equals to 30 in base 10. Thank you for being part of the program. Thank you for watching.